Hi everyone, my name is Fanying Chen and I'm a PhD student at Boston University Westrom School of Business. Today I'm presenting our work on integrating telemedicine with AI-driven dermatological services, joined with my advisor, Professor Avi Seidman and Professor Offer Barrow. In the past decade, we saw a rising number of medical AI systems to assist physicians, especially specialists, as a complementary support. For example, in radiology diagnostics, in digital pathology. However, these medical AI systems are mostly point solutions in the sense that the workflow stays the same. These point solutions are typically hard to sell. Our work hopes to create a system solution to integrate these AI-driven technologies with in-person clinical workflows to improve access to care and to alleviate physicians' burnouts. The system solutions are typically having a much larger impact and are easier to sell. Here we present a case study from a large HMO's pilot experiment. This large HMO serves more than 2 million members, and they recently launched an innovative digital dermatology channel called Teleskin to their members, hoping to improve the resource access. Teleskin works very straightforward. The members download Teleskin on their phone and follow a self-guided tour whenever they need a dermatology service. The average response time of Teleskin is 2 to 5 days, and there's no significant difference in the diagnostic quality for medically eligible cases. As such, Teleskin is well received by the patients. However, there is higher service cost per case used by the Teleskin, which is paid by the HMO. Because no medical AI diagnostic can run without a real physician, so the HMO is paying for the subcontractors that are working for Teleskin on a per-case basis. The managerial question for the HMO leadership is how to optimally design a new system that integrates Teleskin with its existing in-person clinical system. And what would be the optimal policy to offer patients this Teleskin service? And with this new system, what would be the throughput for the in-person clinic and for this digital channel? And how long will the patients wait in this new system? And what will be the impact on the HMO's cost per patient? And how can HMO leverage this new technology on the social service equity? We design a dynamic flow diversion service model to answer these questions. In the dynamic flow diversion service model, there's a main line of service that captures the HMO's in-person clinic. We call it the main line or the ML. And there is an auxiliary line of service that captures the digital channel or the Teleskin service. Whenever a new patient arrives and requests a dermatologist appointment, the HMO compare the current queue length at the main line with a predetermined threshold level N. If the queue length is short, then the new patient automatically joins the in-person clinic and waits for the dermatologist appointment. However, if the mainline queue length is greater than N, then the HMO offers this patient the option to use auxiliary line. Not every patient or every case is qualified for the auxiliary line usage. So we use a probability P to capture the probability whether the patient will or will not use the option if they are provided. In fact, P is a function of both the patient's medical eligibility and their willingness to use Teleskin, and also the time savings by switching to a shorter auxiliary line service. We use a two-dimensional Markov chain for the mainline and auxiliary line system. In this Markov chain, each state ij represents that there are I patients at the mainline and j patients at the auxiliary line. We notice that this two-dimensional Markov chain is asymmetric, and the rates going to the right and to the down are state-dependent. Yet, we derived closed-form results and KPIs for the mainline. Given any predetermined threshold level n, we derived closed form expressions for the steady-state distribution of the main line, and also the expected waiting time for the patient at the main line and auxiliary line. We also derived closed form expressions for the HMO's cost per patient given any threshold level n. This allows us to further do the optimization and optimize for the HMO's most cost-effective option. Here, we provide a data-driven example using the real field data from the HMO to present the benefit of this optimal system. Previously, without teleskin, in a conventional system, patients arrive on average 39 patients per day, and the physician is seeing on average 40 patients per day. Thus, the average queue length at the in-person clinic is about 800 patients, and each patient waits for about 20 days. Now we're adding the teleskin, which is working the same rate as the in-person physicians, with seeing 40 patients per day. And the probability of using this teleskin, if the patient is offered, is not very high. Only 30% of patients who are offered will use the teleskin. So our optimization model gives the optimal diversion threshold level n equals to 45 patients. Whenever there are more than 45 patients at the main line, the HMO will start to offer new arrivals the option of using this teleskin service. Now in the new DFD system, we see that the average wait time for any patient is less than 1 day, and the average queue length is only 25 patients. In fact, only 2% of all patients eventually use auxiliary line, providing a cost-effective solution for the HMO. We can further extend this model to capture the multiple independent clinics that are serving different geographic areas and with different service parameters. This allows us to further address the regional disparity problem. Here is another example. There is an urban clinic. The patient's arrival rate and physician service rate are as before. Thus, the queue length is 800 patients, and the average waiting time is 20 days as before. And there's a rural clinic, which is half of the size of the urban clinic. There's only 19 patients arriving per day, and the physicians are working half of the time, so he's only seeing 20 patients per day. The queue length is the same, but the average waiting time for the rural patients are twice as long as the urban patients. Now with teleskin, the optimal diversion level is different for the urban clinic and the rural clinic. But now both clinics' patients are only waiting for less than 1 day, and the urban clinic has on average 25 patients, but the rural clinic has on average only 16 patients. And 2% of the urban clinic use the teleskin, and 3% of the rural patients use the teleskin. To conclude, we're the first study that focused on the dynamic integration of AI, telemedicine, and in-office specialty care, especially the secondary medicine. And we provide a creative transition from medical AI point solutions to medical AI system solutions. And our field data and queuing analytics shows a cost-effective solution to the long waits problem. Thank you for your time, and I hope to see you at the conference.